here we see that we are not actually learning a new concept for this lesson. We are simply applying the idea of the exponential growth and decay to some other things. And I actually think we've already dealt with compound interest. Compound interest works the same way, but there's not too much in this lesson about that, just a tad. So when we had interest and we were doing continuous compounded interest, this was the formula we used. And in this formula, R was the interest rate. What we're going to kind of shift over and look at is this formula, but actually it's set up the exact same way because we have traded our interest rate for a growth rate, but interest does make the amount of money in the account grow, so it really is a growth rate. And then what this P is your population. But that population does not actually have to be people. It could be just a count of bacteria or a count of rabbits or a count of people or whatever. So that does stand for population. And the population over time, or as a function of time, is equal to the initial population, just like P over on our interest formula was our initial amount. Our initial population times E raised to the KT, where K is your growth rate and T is your number of years. So here is the type of application problem. If you have ideal conditions, a population of rabbits has an exponential growth rate of 11.7% per day. Consider an initial population of 100 rabbits. So as we look at this problem, then this is our growth rate that K is, and I am going to move the decimal, 0.117. And then the initial population of rabbits would be P sub 0, and that's 100. Find the exponential growth function. Now on your homework, you will have problems that ask you to type it in, and when it asks you to type in the function, make sure that you leave a variable in it. The function is P of T, and I actually think they already have that part on your homework. But then when I do P of T here, and I say P of T is equal to the initial population of 100 times E raised to the, now I'm going to put in the 0.117 and leave T. Okay, that's what makes it this function of T. We're supposed to graph the function. All exponential growth always looks like that curve going up, but because we're going to use this formula to do some other questions, I'm going to go ahead and bring up the calculator. Under y equals, I can type in that 100 times E, that's second ln, raised to the, and that was 0.117. And of course, my function on there had a t, but I'm just going to use an x. The calculator doesn't care what the variable is. And then I'm going to hit graph. Now realize when I hit graph, I may need to totally change my viewing window, because this viewing window is only going from -10 to 10, so you would be tempted to look at it and think, hey, it didn't even graph. But actually, you're just not seeing it. So I'm going to hit window, and I know that population never gets negative. I don't even know why I put in 2 zeros there. But so I can start at x of 0, and then I know that I've got to go up considerably because I started with 100 rabbits, but I don't know how far up it's going to go. So let me just put in maybe 1,000. And if I'm going to go from 0 to 1,000, I certainly don't want it to have to count by 1. So I'm going to let it count by hundreds, which means it'll only put 10 lines going on the x's. And I guess on the x's, I started with 100 rabbits. This is how many days it is, so I probably didn't need to go out 1,000 days, but it didn't hurt. On the y minimum, I can do the same thing, and I can say, okay, I don't think I'm going to get more than 1,000 rabbits. If I do, I might need to change that. I'm going to let it count by hundreds. And now let's go back and look at the graph. Okay, so I really didn't need nearly this much on my x-axis. I'm going to go back and change that again and say, well, let's let the x maximum be maybe 15. And I think if it's only going from 0 to 15, it can count by ones. All right, you know how steep it looks depends on how far out you go. But here's a key thing then. This represents the starting value. I know it's only one mark up, but remember, I set that to count by 100. So that's representing 100. And then it's going up. And that's pretty typical. I mean, that's really what we should expect on all of our exponential growth ones. It should be a curve that is headed up, And this particular point is the important one to us because that one is your starting value, okay? And then it's going to go up from there. Now, as far as what the population will be after 7 days or after 2 weeks, that's where you want to go to your table of values is the easiest way. You could redo the problem over and over, but if I'll hit second table, then I should be able to type in after 7 days. So 7 days, 7, enter, and then 2 weeks would be 14 days. So I have approximately 227 rabbits, and then 514 rabbits. So 227 and 514. And then just to clarify, this is my population after 7 days. And this one was the population after 2 weeks or 14 days. So that's how many rabbits we'd have. So, oh my goodness, you start with 100 rabbits and then they're just everywhere, which brings up that common phrase you may have heard, multiply them like rabbits. But it did say ideal conditions. So I love rabbits, but at the same point in time, the reality is they don't have ideal conditions. That's where they're dealing with, you know, is there enough food? Is there enough shelter? Or do they have predators? If we had ideal conditions, this says find the doubling time. And then you're going to have quite a few problems in your homework where it asks you something about K or T or the doubling time. Because these little equations, it's going to be easiest for you if you just kind of memorize these. K times T is equal to ln of 2. Now, the reason this happens, and you may not care, but, you know, I'm a teacher, so I'm going to show you, is that if I started with 1 rabbit, when it doubled, I would have 2 rabbits. And then this is a KT up here in the original formula. It really doesn't matter what I'm dealing with, rabbits or anything else. I can have my growth thing times time. Well, this one had no real effect on it. So I can do e to the KT. And then you'll remember from our previous thing, if we want to solve one of these, we can use an ln. So ln of 2, that's because this is in base e, will equal KT. And now I can just stop because you can see that's actually what this first formula is. All 3 of these formulas are identical, really. They've just been rearranged. So if you take both the left hand and right hand sides of this equation and you divide by K, then you would get this last one, T equals. On the other hand, if you divide both sides by T, you'll get this middle one, K equals. So they all come from this particular formula. So anytime you want to know the doubling time, you can just do ln of 2 divided by the growth factor, and that's really then this one. So I'm going to say, okay, ln of 2 divided by, and the growth factor as a decimal, 0.117. All right, and the doubling time tells you how many days it takes to get twice as many rabbits. So back in here, if I quit this, and I can say ln of 2 divided by that growth factor. Rabbits double, the number of rabbits double about every 6 days in ideal conditions. So this is approximately 6 days. Now you'll have maybe something else, but it's going to be very common for them to ask you to find the doubling time or find the growth factor if you know the doubling time. And so that'll be a simple division problem, okay? But since we don't really have ideal conditions, I mentioned earlier that we can have predators or we have a lack of food or something, and this is true for everything. People try to solve their limiting conditions. You know, like if people feel like they're running out of living space, then they're going to make buildings taller because they're running out of land. Then countries work to increase food production. But not all things have it where they can just solve their limiting value issues. So we have a level where we just kind of see that population level off. And this is one of those types of formulas that's going to level off, and it's called a logistic function. Now, one important thing I would tell you to point out is that as t heads to infinity, then y is going to then we're going to have this horizontal asymptote. The way that's going to be written in your homework a lot of times, and they're going to ask you this question more than once, so you want to look for this phrase, as t heads to infinity. And it could say n of t, because sometimes they use n for number, or it could say p of t like I have up here, but your function value heads to that limit. Now, when we say it heads to the limit, we don't necessarily think it's going to cross it either. Okay, so could it cross it? Well, sometimes a horizontal asymptote gets crossed, but in this, you're going to really be looking for this phrasing on the homework. Okay, t is going to head to infinity, which means as t heads over to the right, n of t is going to head over to that level. So we've got an example that's got some numbers in it on our next slide, and we're going to look at what this logistic factor looks like when we do have limitings in there. So here's one, and what happens is that if we have a population of 3,500, then when a disease starts to go through this particular community, we know we can't ever get more than 3,500 infected. That's all there is. So that's where it's going to level off at. So I'm going to pull up the calculator and punch this in, but I will certainly have to change my viewing window again, because this is going to go up really close to 3,500 on my y-axis. I'm going to go to y equals, let me kind of maybe get this over here where I can type it in and see it. So alpha y equals enter, so I can put in a fraction. I've got 3,500 for my numerator, and on the denominator 1 plus 19.9. Now you're always going to have that 1 plus. That was on our just previous slide, but the other values are going to change. 1 plus 19.9 times e to the, which is second ln, e to the, negative 0.6, and then my variable I'll use an x. Okay? So when I go to graph this, I know right now I'm not going to be able to see it. I'm going to go ahead and change my window, because that 3,500 is going to be the high value. So here before, where I was looking at 1,000 rabbits, I'm going to go ahead, and I want it to go past it some just so I can see it level off. So I'm going to put 3,600, and I'm going to let it count by 200s. Okay, so it'll go from 0 to 3,600, and every mark on my y-axis will represent 200. Now, I don't know how many days I'm going to need to go out, which is x is representing time, but I certainly don't need negative time, so it's fine for it to start at 0, but maybe I want to go out an entire month, so I'm just going to put 30. Now let's see what this looks like. Okay, now remember, I went up to 3,600, that's why you're seeing it right here. And I was counting by 100s, so it looks like it's starting at about 100, but I don't know for sure. But that's the shape of the graph, and that is what you should expect the logistic functions that have that limiting factor to look like. They're all going to come over and go up and then level off. And this is the value it starts at. So this is the value when your time is 0. So as t goes to infinity, they level off at a horizontal asymptote, and that horizontal asymptote will be this number up here, which is where we had an a in our original equation. So graph the function. This is kind of what it looks like. Now, how many are initially infected with t is equal to 0? This is where that table of values is so handy on the calculator. That's going to be second graph, and I can put in 0, and so if I put in 0, you see that we started with really about 167 people. And before I even write that down, it asked me, find the number infected after 2, 5, 8, 12, and 16 days. So I'm just going to get all those up there. 2, 5, 8, 12, and 16 days. So here I'm seeing this number of people. And let me just kind of move that so that maybe I could write it down. At 0, it said approximately 167. Now, going to my other values, I have 500 at 2 days. At 5 days, it said 1,758. and then 3,008. I'm rounding this off to a whole person. Don't want to have part of a person infected. Make sure on your homework you're always looking at what they tell you to round it to, but on something like this they'll probably say an integer. And then I have 3449. Okay, and let me just bring that back so you can see those numbers again. I was just copying down numbers from here and rounding it to a whole number. Okay. Now the last question says, using this model, can you say whether all 3,500 people will be infected? Explain. Well, now, certainly in real life, you could end up with everybody infected. But using the model, we're going to say no, because on our equation, what's really going to happen is we have an asymptote here that we're getting closer and closer to, but we don't reach it. So it approaches would be how they would probably say the word or phrase this. It approaches 3,500, but doesn't reach it. Now, again, the model is not exactly like real life. Certainly we could get everybody infected, because I'm thinking about the time you get everybody but this extra 50 people, they've probably been exposed. But maybe they just don't get it. I don't know. But doesn't, so we're going to say it doesn't reach 3,500. Okay, so using the model, it doesn't reach it. It might in real life. Now that was about increase. When we have decrease, we actually have the exact same kind of a thing, only instead of a growth rate, K becomes a decay rate. And we have a negative here. The negative is what makes it go down instead of go up. So you do have some carbon-14 problems in your homework, and that's why I particularly wanted to do this problem. According to archaeologists, carbon-14 has a half-life of 5,750 years, which means however much something starts with, 5,750 years later, only half of it's left. And if you think about what they mean by half-life, you know, you just think if you put an apple outside, eventually it's going to rot. How long does it take it before it's half gone? That's sort of a concept, but we're dealing with an element, something different here. So as we look at this, they tell us that they have found a tomb, okay, and it contained 5 wooden sarcophagi that contained mummies. The archaeologists believe the mummies are from the 18th dynasty, which was 3,300 to 3,500 years ago. So we have 2 values for time here. And it says determine the amount of carbon-14 that the mummies have lost. All right, so something that's kind of tricky about this, just kind of keep in mind. This formula is not set up to tell me how much they've lost. It's set up to tell me how much they have. It's going to tell you how much remains after a period of time. And so when we do this, we just kind of have a few little steps. Now, first of all, I have a note down here, find K first. This problem did not tell us the rate, so we have to find K. This is the exact same relationship, even though now we have a decay rate. So just like before when we were doing growth rate, we said K times T is equal to ln of 2, and then we could use these. If I want to find K, I need ln of 2 divided by T. So that should look familiar just like we did it before. So if I want to find the decay rate for this particular problem, I need to go up and say, okay, I'm going to do ln of 2 divided by T, and notice that T is how long it takes half-life. So I'm going to say 5750, and that's going to give me a carbon-14 decay rate. And when you have other carbon-14 problems, you can use the same decay rate that we're about to find here. So let me just bring the calculator back over. And we're going to say ln of 2. I could have put this like a fraction, but I'm just doing ln of 2 and then divided by 5750. Now this e to the negative 4 means you need to move that decimal 1, 2, 3, 4 spots around that. So if I put 1.2 e to the negative 4, we get about 1.2, and it said e to the negative 4, which really means it's in scientific notation. And I need to move that decimal 1, 2, 3, 4 spots. So I'm going to end up with 3 zeros in front of that 1 and 2. So that's my decay factor. So now that I know the decay factor, we're needing to find the amount that they've lost, and what we're going to do is find the percentages, because I don't have anything about a measurement of any sort of grams or anything like that, so percentages is really my only option. And I know that they started with 100%. So I'm going to use P sub 0 as 100. If that's 100, I also know my time. Down here, I have two values for time. So I can say, well, P of 3,300 is equal to, and now what I'm going to do is I'm going to bring up my calculator again, and I'm going to put in the K value I just found, as well as the T, that very first T value. So on the calculator, I'm going to go 100 times E, which is second ln, to the negative 0.00012, then times my T, and my very first one was 3,300. So I have taken this. I know I started with 100%. When I click enter on here, it's going to tell me the percent that's left. It's going to tell me the percent after 3,300 years. So I find that it's approximately 67.3% remains. Well, they didn't ask me how much remains. They actually asked me how much they lost. So I need to do 100 minus 67.3 to find out how much they've lost. And I find that they've lost then 32.7% if they're actually 3,300 years old. So 32.7% lost. But the thing is, we're not sure that they're 3,300 years old. They might be 3,500 years old. So I need to repeat this process with 3,500. And on my calculator, I'm going to go up so that until this is highlighted, and then I'll hit enter. And that lets me copy and paste it. And I can back up and simply change that to a 5 right there. So for 3,500, they started with 100%. How much remains then after 3,500? 65.7%. So this one then will be 65.7%. And again, that's what remains. They're asking me what's lost. So 100 minus that 65.7. Okay, so 100 minus 65.7. I know that's not on screen right now, but I'm just clicking it into my calculator. And that comes out to 34.3%. So you can use percentages for those populations also if they don't give you any sort of a measurement. How much carbon-14 have the mummies lost? I actually have, because they had 2 different years, I have 2 different values here. They've lost somewhere between 32.7 and 34.3% of their carbon-14. So just remember, if you will have a carbon-14 problem, you can use that same K value for the decay. All right, let's look at this last little problem. Another thing you have on your homework is a chart. And it'll come to you one little question at a time, but they will either give you the decay rate or they'll give you the half-life. Now, it really doesn't matter if you are needing to find K or T. In order to do that, they're both ln of 2 divided by the other one, right? That's fine, because we're going to do ln of 2 divided by. So for this very first one, let me go ahead, alpha y equals, enter. And I have ln of 2 divided by 3.1. Now, if I could write that on the screen right now, which it's not letting me do, I would move this over for a percentage. So I would say that this one is approximately 22.4%. Now make sure when you're doing these, you very, very carefully on the rounding, because it seems like some of these on the homework ask you to round to one place after the decimal, and some of them ask you to round to 4 places. So you've got to read that real carefully. But this would be then, depending on what you needed to round to, 22.4%. The next one, I'm going to do it the exact same way. So the easiest thing for me is just go up and hit enter, so I can just change my number that I need to change. It's still ln of 2, but now I'm dividing it by 22.3. And now it's in years. And your decay rate and half-life are always measured in the same units of time. So if it's minutes, it's minutes. If it's years, it's years. Okay, so lead, which we know lasts a long time, right? It doesn't decay easily. It will slowly rust and eventually disappear, but not where we're going to see it disappear. We just see a little bit of rust. Well, that's because the half-life is so slow. Not like carbon-14. But anyway, this one comes out to be 3.1%. 3.1%. Now on the next one, though, I've got to go the other direction. They gave me a per day decay rate, and they want to know the half-life. So it actually still works the same way, but do remember now moving the decimal the other direction, so that's going to be 0.0115. And this one's half-life for iodine would be 60.3 days. Okay, 60.3 days. Again, we had one here measured in minutes, one's in years, one's in days. They're always consistent. So if the decay rate's in days, half-life is in days. Half-life is in years, decay rate's in years.